Assalamu alaikum everyone. This is week 6 lecture and we're gonna talk about data representation. The meaning of data representation is how do we represent all the form of data in our daily life in the computer. So in this lecture we will know the two ways of storing data electronically. Then we're gonna know that computer know only binary numbers, so we're gonna define the concept of binary number, and then we will try to differentiate between decimal number and binary number and how do we convert from decimal to binary number. We also gonna talk about how the character and the text are represented when saved on the computer and how the sound and image are also saved on the computer. And at the end, since we have different data type, we wanna know how the computer can differentiate between these different data type. So data can be stored electronically in two ways, either analog or digital. Analog are represented by the continuous wave like the sine wave, where digital is discrete in nature. The signal is our way of sending the information from one device to another. So again, what do I mean by analog signal? Analog signal is a continuous wave that keep on changing over time, and it's represented by the sine wave. And I would say that think about the analog signal as infinite set of possibility or of value. Because a continuous in math means that I have infinite set of value. In regard to digital signal, it is discrete. Discrete, that means like I have a finite set of value, and in case of the computer, we usually represent the information in a form of two values, and they are 1 and 0. And we represent the digital signal by the square wave. So analog is continuous in nature, and the idea is if you want to know the value in a point of time, you wouldn't know the exact value, you're gonna get an approximation. But in the digital signal, since we have a finite set of value, it's gonna be either 0 or 1. It's not gonna be something else. But here it could be 2.5, 2.3, and whatever, because we have infinite set of value. So in our life, we communicate with each other with analog data. If we think about number, we have infinite set of number. We don't have a limit for the number. Also the letter, we have Arabic, we have Japanese, we have English, and the image are also infinite. Like there is some image that are available now, and there is image that's going to be produced in the future. And we have multiple sound, and also if we think about the color, we have infinite set of color. So how can we represent these analog data in the computer that can only understand two values, which are the 0 and 1? And also the computer is limited by the capacity. So like if I have infinite possibility, how the computer can store these infinite possibility? So to explain, obviously the computer cannot store infinite possibility, but we will understand how the computer can store these different possible value in a representation of 0 and 1, and that's why we need to talk about the binary number. To explain the idea of binary number, let's talk about a system that uses an idea similar to the binary number. This system is called Lewis Braille system. If you know Braille, he is a person who is blind and he created a language for the blind people. Lewis Braille system is an early example of binary representation of data. So what do I mean by binary? Binary mean two. By using two symbol. If we're gonna look at the Braille alphabet way of representing the character of English, we can notice that we have two symbols. Is denoted by the black dot, and you can see some dot here that they are wide or they are flat. So actually the blind person cannot see, so he use or she use her hand to and touch these symbol, and based if it's raised or flat, they can know the difference. So Braille alphabet use a combination of these raised and flat symbol to make the alphabet of a Braille, which is the language for the blind. So in regard to Braille alphabet, we will understand that Braille alphabet is consist of 6 dots. Why Braille use the 6 dots? It's gonna become apparent if we go over the examples. Let me remember that we are trying to make a characters, or we make a representation for the blind people to differentiate between different characters. So let's say that actually I have one dot. If I have one dot, what is the possibility for this dot? The possibility for this dot, it's either to be a flat or raised. And in the following example, I will replace the flat and raised by the color. So like one of them is gonna be white and another will be black. So if I only have one dot, what is the different possibility that I will have with this dot? You would tell me the different possibility is two, which are the dot will be white or the dot will be black. So the number of unique possibility is 2. How about now if I have 2 dots? If I have 2 dots, the possibility is that both 2 dots will be white. And let's assume that I'm gonna represent number 1 to be the dot that they are white. Now let's look at the second possibility. I would say the first one is white, the second one I will gonna make it black. The third possibility is that I'm gonna make the first one black and the second one white. The fourth possibility is to make both of them black. As you can see, this is unique and this is the number of possibility. And by these 2 dots that they could be either white or black, I can make a system that represent 4 value that could be 1, 2, and 3, and 4. Now I want to tell you, how about if I increase the number of dots to 3? How many possible value you will have? To explore that, let's work on this example. So I already have here with the 2 dots is 2 white. Now with this example, how many possible way I can create with the 3 dot? You would say the third dot I can make it white, or the third dot I can make it black, which is the same here. So like the 3 dot will be white, or like the first 2 dot is white and then black. Now I'm gonna come here and also I will say the first one is white, then black, and now I have 2 options. For the third white, either to make it white or to make it black. The same goes for this one. I have black, white, so I have an option to make one white and another option to make it black, which is here. Black, white, white, black, white, black. For the other option, here in the previous one, I have already two black. What is the other option that I have is to make the third one white, and in the other option to make the third one a black. If I told you how many the number of pattern, the unique pattern that you will have with the three dot, it's gonna be 8. And so as I said, with the three dot, we're gonna get 8 pattern. If I know the number of unique pattern that I'm gonna use to represent my system with the previous number of dot, like for example with the braille with 2 dot is 4, and the question is asking you how many pattern you will get with 3 dot. The thing that you will do is you're gonna multiply 4 by 2 to get the 8 pattern. So if you know the previous pattern, you can get easily the number of pattern if you increase only 1 dot. Because and why it is the twice? Because like when I go in every possibility in the previous pattern, I said we have two options, either to make the dot white or to make it black to make a unique pattern. So with 3 dot, we're gonna get 8 pattern. With 4 dot, we're gonna get 8 multiplied by 2, which is 16. With 5 dot, we're gonna get 16 multiplied by 2, which is 32. And with 6 dot, we're gonna get 32 multiplied by 2, which is 64. So this means that the Braille alphabet consists of 64 unique pattern. Why the Braille system needed the 6 dot? Because the 5 dot can represent only 32, and 32 were not enough to represent the whole language for the blind people. So again, as I said, if you know the previous number of pattern and you increase the dot by 1, every time you add an extra dot, that give you twice as many pattern. But if they give you the number of a dot and they say that the system is binary, you can use this formula. The formula says the number of different symbol to the power of the number of dot. So we know it's a binary system, so the number of different symbol is going to be 2. So 2 to the power of the number of dot. If I say the number of dot is 4, I would say 2 to the power of 4 is going to be 16. So if I have 5 dot, 2 to the power of 5, it's going to give me 32, because it's 2 multiplied by 2 5 times. So a Braille system, as I said, sets an early representation of binary system, and binary use two symbol. The computer device use a similar representation called the binary number. The binary number is the way that the digital devices are used to save and manipulate data. In binary number, all the value are represented using only the two binary digits 0 and 1, which we call them bit. So 0 is 1 bit and 1 is 1 bit. To distinguish the binary number from the number that we use in our life, that we're gonna call them the decimal number, we're gonna use the subscript 2 in the number. Like if I didn't put this subscript and I told you to read this number, you would tell me 1000, 100 or 1. But with binary number, it's just 1101. In the other hand, we have number 13 here. Number 13 is a decimal number because of the subscript 10. So the binary system is like any other system. The numbering system that we know is called the decimal system. Why we call it the decimal system? Because it has base 10, and 10 is the number of different symbols. Because we have 10 possible value from 0 to 9. All number in the decimal system can be produced by a combination of 0 to 9. In binary system, the number of unique symbol is going to be 2, and the base is 2. Why? Because we have only two possible values, which are 0 or 1. The same as in any base, 0 digit has non-contribution. So like if you add 0 to the 1, it's going to give you 1, where 1 has a contribution which depends at the position. So I think you remember this game for the children. If I ask you what is the number in here, you would say it's 3,122. And why you did that? Because you know this is the thousand, this is the hundred, this is the tenth, and this is the ones. So another way to think about how did we do the math for it is that we say that the number here is multiply by 10 to the power of 0. 10 to the power of 0 is 1. That's giving me 2. Then I came here. This is 2 multiplied by 10 to the power of 1. 10 to the power of 1 is going to give me 20. Now I'm going to come to the 100. 100 is because like I have only one ring here, it's gonna be 1 multiplied by 10 to the power of 2. It's gonna be 1 multiplied by 100, which is 100. And then here in the 1000 I have 3 rings, and since it's 1000, it's 3 multiplied by 10 to the power of 3. It's gonna give me 3 multiplied by 1000, which is 3000. And the thing that we're gonna do is gonna sum the result as here. So 2 plus 20 plus 100 plus 3000, it's gonna give me 3122. To get the value in binary numbering system, we say the binary numbering system has a base 2. And it's base 2 because we have only two the value, which are the 1 and 0. And each position, similar to this decimal, is a power of 2, while in decimal it's a power of 10. So if I want, so this number here is in binary. If I want to know the value of this binary number in decimal, I would do the following procedure. So this is the number. I'm gonna come from the right to the left. From the right, the first bit is 1, and I would say 1 multiplied by 2 to the power of 0. 2 to the power of 0 is 1, so 1 multiplied by 1 is going to equal to 1. Then I'm going to go to the second digit from the right to left. It's in the second position, so it's going to be 0 multiplied by 2 to the power of 1, which is 0 multiplied by 2. And we said 0 doesn't have a contribution on the summation, but in the multiplication, usually it's gonna remove whatever here, so it's gonna be 0. 1, then we go to the third digit, it's in the third position, and in the third position, 1 multiplied by 2 to the power of 2, it's gonna be 1 multiplied by 4, it's gonna give me 4, and then for the fourth digit is 1 multiplied by 2 to the power of 3, and 1 multiplied by 2 to the power of 3, 2 to the power of 3 is 8, so 1 multiplied by 8 is gonna be 8. If we sum them, 1 plus 0 is 1, 1 plus 4 is 5, 5 plus 8 is going to be 13. So this binary number is a representation of number 13 in decimal. So again, computer are electronic device and they only know 0 or 1. Why they know 0 and 1? Because we are talking about electronic device which know the switches which is 0 and 1. Binary coded are device. So like the binary code that we saw here were devised to represent a specific decimal number which was the 13, and we use the binary code to represent not only number but also letter, color, sound, and image, as we will see in this lecture. So each 0 or 1 is called a binary digit or bit. By placing them side by side, we can create a binary code. So if I have the binary code here 0 and I told you how many number of bit, you would tell me that this 0 is have 1 bit. It could be that this binary code here is not 0, it could be 1, and again the number of bit is going to be 1. In this example, the binary code is 1, 0. If I ask how many number of bit, is 2 because it's having 2 bit next to each other. The binary code here is 1011. If I ask the number of bit, it's gonna be 4 because it's the number of bit. I have 3 ones and 0, and so on. So, if we increase the number of bits, and I want you to make a connection that the number of bit is similar to number of dot in a Braille system. So if we increase the number of bit, we can increase the number of unique binary code, and we can use this binary code to represent more data. So if I have 1 bit, if you remember the formula in the Braille system, it says the number of unique symbol, and since we are using binary, the number of unique symbol is 2, and then the number to the power of the number of bit. So here I'm gonna add the number of bit. So if I have the number of bit to be 1, the number of possible value is going to be 2. So here I have the decimal number 0 and 1. 0 and 1, I can represent them using only 1 bit binary number. So I can represent the 0 with 0 and I can represent the 1 with 1. But if I come to number 2, I cannot represent it with 1 bit. I need to, in order to represent it, I would need 2 bit. And again, if my system is a 2 bit, it's gonna be 2 to the power of 2, which gonna be, which mean like my system can represent 4 value. So in this case, I can represent 0 as 0, 0. I can represent 1 as 0, 1. 0, 1, and I can represent the 2 as 1, 0. I can represent the 3 as 1, 1. If I come to number 4, because the 2 bit is not enough, I would need to increase the number of bit to 3. So with the 3, I can represent the 0 in this way. I can represent the 1 in this way. I can represent the 2 in this way, the 3 in this way, and so on. So this is the 100 is the 4, 101 is the 5, 110 is the 6, 111 is the 7, and number 8 is cannot be represented with 3 bit. I would need a 4 bit. So with this formula, like for example 2 to the 3, it's gonna give me 8 unique pattern, but I know that I start from 0, so the maximum number I can represent with a 3-bit is gonna be number 7. So the process that we take to convert analog data to a sequence of 0 and 1 is called digitizing. From the number example, we can see that the computer can handle data as long they are presented in binary form. The analog number have become now digital data, and not only the number, we will see also the text, the image, that we need to make them digital data. If it was possible to create code to represent all our analog data, it would appear as a group of 0 and 1. And the computer will able to handle this data. So the conversion from the analog to the digital data is called digitizing. This word here. So here is some example of converting a binary number to a decimal equivalent. We denoted the binary number with 2 to differentiate between, and here it's gonna be 3 in decimal, 10, 13 in decimal, and so on. So this is the number 1 1. The procedure is that we're gonna start from the right to the left, and each position, since this is a binary number, each position is a power of 2, and we start with the power of 2 to the power of 0. So in this example, 1 multiplied by 2 to the power of 0 is gonna be 1 multiplied by 1, which is 1, and then we're gonna come to the 1 here, which is 1 multiplied by 2 to the power of 1, which is 1 multiplied by 2 is going to be equal to, then we sum them, is going to give us 3, as we saw here, that 3 is in binary is 1 1. The same goes for this example. This number is in binary, so we start from the right and we multiply by the power of 2 based on the position. So here 1 multiplied by 2 to the power of 0 is going to be 1 multiplied by 1, which is 1. Then we come here, 1 multiplied by 2 to the power of 1, it's going to give me 1 multiplied by 2, which is 2. Then I'm going to come here, 0 multiplied by 2 to the power of 2 is going to be 0 multiplied by 4, which is 0, and the same go here, because 0, if it's multiplied by anything, is gonna give me 0, but I need to make sure that I multiply it by the correct position so I don't have a confusion with the second bit. Even here, I'm gonna come here, 1 multiplied by 2 to the power of 4, and 2 to the power of 4 is 16. Then I'm gonna sum the number here. 1 plus 2 is gonna be 3, plus 0 is a 3, plus 0 is a 3, plus 16 is gonna be 19. The same goes here, and you can do it by yourself. This is in regard to number representation. Now let's talk about character and text representation. Character representation. The character is a single letter, and usually in the programming languages we denote it by a single quotation. If we want to talk about how do we represent a character in the computer, there is no natural correspondence to binary number. We cannot say like the same as when we talked about the decimal number, and how do we get the value of the decimal number. In the same way, how do we get the value of the binary number in regard to the decimal number. For this reason, the computer scientists devise an arbitrary system for representing character as a bit pattern, and this system was called ASCII, American Standard Code for information interchange. It is a scheme used to represent only the American character and punctuation in addition to the digit. Each character in this system will be represented by 8-bit of pattern. The 8-bit of pattern or 8-bit, if we have 8-bit, we usually call the 8-bit 1 byte. So each letter or each character is represented by a binary code that consists of 8-bit. All the digits are contiguous as our lower and uppercase letter. We're gonna see that this binary code representation, actually if we take this binary code and we convert it to a decimal number, it's gonna give me a specific number, but this number for 0 it's gonna be less for 1, and the number 8 is gonna be less than 9 in a decimal. Also, if we're gonna take the binary code for the A, the binary code is gonna be, if we convert it to decimal, it's gonna be less than the binary code of B. So in the programming languages, if we use something like this, is the character 0 is less than 1, this is gonna be a correct statement, and we can use it in the programming language. Again, the ASCII is only for the American character, is 8-bit. So if I ask you what is the number of unique pattern that 8-bit can give me, you will use the formula, which is 2 to the power of 8, and 2 to the power of 8 is gonna give me 256. 256 is not enough for all the character in the word. That's why, or it's not enough for other languages, like for example Japanese, Chinese, and Arabic. That's why they define the Unicode. The Unicode is another scheme, another representation. It's an extension to the ASCII. It's used the 16-bit, and so the number of the unique character in this scheme, it's gonna be 2 to the 16. And I mean, when I say it's 16-bit, that's mean like each character is represented by binary code that has 16-bit on it. So the Unicode is a 16-bit pattern, and it supports other language in addition to the English. If you remember here, when I talk about this, I said that the 1-bit is able to represent the 0 and the 1. The 2-bit is able to represent the 0, the 1, the 2, and the 3. The 3-bit is able to represent these things. It's the same now with the Unicode. The Unicode is able to represent the English character, but in addition to the English character is able to represent the other languages. But the difference between the Unicode and the ASCII is the way of the representation. So in the ASCII we use the 8-bit, in the Unicode we use the 16-bit. Again, in the ASCII and the Unicode representation, we have digit, we have uppercase letter and lowercase letter. The digit is gonna be binary code, but if we're gonna take the binary code and we convert them to the decimal, we're gonna see that 0 is gonna be 48 and 9 is gonna be 57. So 1 is gonna be 49 and so on. In regard to the uppercase letter in ASCII. So this is in ASCII. If I'm gonna take the A, for example, the capital A, the binary code of it, if I convert it to decimal, it's gonna give me 65, and the Z is gonna be 90. And the same is for the lowercase letter. The small a is gonna be 90. If I convert the binary code to decimal, it's gonna be 97 through 122, which is gonna be the small z. Okay, that's why the ordering is important and enable program to and programmer to perform comparison of character value, like if A is less than B. So like if I want to make a sort for the name, I can compare the first letter in the first name with the first letter in the second name, and I would say if the first letter in the first name is less than the first letter in the second name, that's mean I'm gonna put it in the sorted order first. Again, I said that each character in ASCII is a binary code that consists of 8 bits. So even the space is a character that has a specific code. So the A here, this is the binary code for it, and if I convert this binary code to a number, the value of this binary code will be 65. I hope it's clear right now. So when the computer keyboard is being used, the ASCII code are sent to the computer as the character are typed. So this is the ASCII code will be sent to the computer. The computer will combine the stream of bit into bytes, and again, what do I mean by bytes? It's 8-bit. It's a collection of 8-bit. So the thing that's gonna happen, that the computer will divide this to like it's gonna count 1, 2, 3, 4, 5, 6, 7, 8. So this is the first character and this is the second character, and if it's longer, this is what's gonna do 1, 2, 3, 4, 8, and then it's gonna say this is a character. And then take this first part, and if we take this first part and convert it to decimal, it's gonna be 84, and 84 will be the capital T. And if we take this number here and we convert it to decimal, it's gonna be 52, and 52 is the digit 4. Another way is that we're gonna go to the table here, and we're gonna see what is the code. We're gonna find the code here, and we can see the corresponding here. So the A letter, when you type the A letter in the keyboard, this is the thing that's gonna be stored in the computer, this binary number. String, on the other hand, are a sequence of character. It's a collection of character, and so they are a sequence of ASCII code, one for each character in the string. So if I have the string, and again, also the string, we use the single quotation or the double quotation in the programming language, and again, this is the way that it's going to be represented by a sequence of ASCII code. So the if, this is the code for it, or this is the code for it, and so on. And again, each ASCII code is represented, each character is represented by 8-bit or 1 byte. So 8-bit mean 1 byte. So if I ask how many bytes do you have in this string, you will say 1, 2, 3, 4, 5, 6. I have 6 bytes. If I ask you how many bits you have in this string, it's gonna be 6 multiplied by 8, which is 48. Okay? Let's talk now about color representation. Also, color are represented using a sequence of bits. With one bit, we can represent two colors. With one bit, we have two possibilities, either 0 or 1, and that's why I will have two possible colors. With 2 bit, I can represent 4 possible colors. With a 3 bit, I can represent 8 possible colors, and so on. If I have 32 bit, I can represent 2 to the power of 32 color. And it's same applying here, like how I know it's 8 because it's 2 to the power of 3. For example, I can, if I have 2 bit, I can represent 4 color. The 00 could be white, the 01 could be the light gray, the 10 could be the dark gray, and the 11 will be the black. Why here is saying off? It just like is a metaphor for how the computer is going to work. The computer is a switch, use a collection of a switch, the transistor, and the 0 is representing when the switch is off, and the 1 is representing when the switch is on. Let's talk now about image representation. Image also need to be converted into binary in order for the computer to process them so they can be seen in our screen. Images are made up of pixels, and what I mean by pixel is this square here. So in reality, you don't see the screen, you just see the space here with a white background. But here we just want you to understand that actually each image, the image is a collection of pixels. So pixel is a small area with associated coordinate location. If we are here in the XY coordinate, we can say that this, for example, is the pixel that's available in point 0, 0. This is the idea of the pixel, okay? Sometimes it's like this, sometimes it's inverted in the programming language, maybe sometimes it's from here, this is the thing that's considered 0, 0. But anyway, this is related to programming, but this is the idea when they what they mean by the coordinate location. It's this part, this is pixel, this is pixel. Each of these squares are considered pixel, and they have a location with X and Y. If it's 2D picture, if this is what I'm talking about. So each pixel in an image is made up of binary number. To create a picture, we need to have a grid, and the square can be colored based on the number of bits that this image is having. But before a grid can be created, we need to know the dimension of the grid. So the dimension of the grid is an example of something we call metadata. And metadata is a word to represent data about the data. It's an information that we want to know about the data. So for the image, so for the computer to create an image, they need some data. And one of these metadata is the dimension. The dimension of the image, for example, is 1200 multiplied by 946. This gonna create for me an image that have the width 1200 pixel and the height 900 for 64 pixel. What do I mean by metadata is all the data that we get about the image. If you right click on the image and you went to detail, these are example of the metadata. So it is information about the data and that we have now, which is the image. Like all these information here are example of metadata. So if the dimension of the image is 10 by 10, this means that the picture will have 10 pixel here and 10 pixel here. And if I'm gonna ask you what is the total number of pixel that this image have, it's gonna be 10 multiplied by 10, which is 100 pixel. So actually, again, this picture here is a representation of an image that has a white background. If we zoom the image enough, we can see that the image is pixelated in this way. And if the image is only black and white, this image is represented only with one bit, because one bit is able to represent two values, which are the black and the white. So if this image here, as I said, it's a white background, and usually you will not see the pixel. This is if I zoom it, and if I zoom it, we will see that here, for example, the 0 is a representation of the white and the 1 is a representation of the black. So from our understanding that each pixel will have a certain color, and this color will be represented by a bit code. Image quality is affected by the resolution of the image. What do we mean by the resolution? The resolution of the image is a way of describing how tightly back the pixels are. Or in another way, it's the number of pixels the image have per inch. And the resolution of the image will depend on the camera that is taking the image. If the camera is taking a large number of pixels per inch, the resolution of the image will be bigger. In a low resolution image, or if the camera is taking a low resolution image, the image will have a very few pixels per inch. And if we try to zoom it, the image first of all will be kind of small, and when we try to zoom it, it's gonna look pixelated as the image here. And we will see that the actual creation of the image, which is consisting of pixel, so we can kind of see the square. But if the image has a high resolution, which means has more pixel per inch, the image will look okay even if we stretch the image and zoom in. But the downside of having more pixel is that each pixel will have a binary code, and it's gonna depend on the number of bits in that binary code. So like if it's white and black, I have only one bit, but I mean like if it's colorful, it's gonna have more bits. And the downside of having more pixel with more color is that the file size will be bigger. All form of data that we see on the internet, image, video, etc., are compressed. And why they are compressed? Because we want to reduce the size of the data to ensure faster transmission between devices or over the internet. Choosing the correct format and compression is a major factor to determine the image size on the disk. That's why we have two compression types. The first compression type is called lossless, mean even if I compress the image to make the file smaller, no information is lost in the compression. This is an example of compressing the image in lossless format. Loosey mean that information is lost in the compression and it's not fully reversible. So the idea of compression is that I try to compress the image so like the file size will be smaller. So if I save it on the hard disk, it's gonna be smaller. But when I open it again and load it to the main memory, if it loosey, I lost the information with the compression, so I'm not gonna get the previous image that I compressed before the compression. But with lossless, yes, the file size will be a little bit smaller, but when I open it in the main memory, it's gonna return back. It's gonna return back without losing of the information. That's why here it says loosey, it's not fully reversible. But the loosey compression format is more efficient in decreasing the size. So we can see the difference between the loosey and the lossless compression. If you are a professional photographer, you most likely want to use the lossless format because like the highlight here may be important for you. But we can see here in the loosey format, still we know this is a kiwi and kind of or maybe these details are not important for us. Is not like really changing the information in a bad way. But again, the loosey format, the file size will be smaller. The lossless, it's gonna try to compress the image but and make the file size a little bit smaller, but it's not gonna be smaller like the loosey. So let's talk about the most common image compression format. The most common image compression format is we can see them when we click on the image that it's stored in the computer and we click on the information. Usually it's the extension of the image. So we have an image dot, for example, something. So the first type is called GIF, a graphic interchange format. It's a lossless format. That means when we save the image, we are not losing any information. We are not losing any information. But the downside of the GIF compression format is it has only 8-bit per pixel. 8-bit per pixel, that means that the color range for the GIF is at most is 256. GIF is used for precise pictures such as line, drawing, and usually used with animated picture. So if you see an animated picture like the one here, most likely it's gonna be GIF. But you can see that the color range are not a lot in compared to the other compression format. The other example of compression format is the PNG, the Portable Network Graphic. It's also a lossless format. The advantage of PNG is it's allowing more color by providing more number of bit per pixel. So the PNG can have 8-bit per pixel, can have 32-bit per pixel, and it can have 46-bit per pixel. what we are using the PNG for. Usually the PNG is used in the logo and text with and it's work best with a transparent background. That's why it's usually the case that you will see this kind of format with PNG, because this thing at the back is represented of the transparent background, and this is actually the reason of the number of increase the number of bit, because it support the transparent background in really nice way. So if you take a screenshot in your mobile phone and you look at the extension of the image, you will notice it's PNG. And the reason for choosing the PNG for the screenshot is because most of the time the screenshot will have a text, and if we use a different version we will lose some information. So we can see that the text will not look clear as in PNG. GPG is also another example of image compression format. It is a lossy format. The number of bit per pixel is 24 bit per pixel. So we can see that the range of color is less than 64, less than the PNG. But the advantage of GPG over the PNG is the lossy format, so the file size will be smaller. Usually the GPG is used in photography in digital camera. So when you are taking a picture in your iPhone in digital camera, usually the GPG is used, but it's not good for a line and text because it's a lossy format. So when you are saving the image with the text or line, we can see some distortion on them. The GPG does not support animation or transparent background. So if you are creating an image and you want to have an animation, better to use the GIF, but you will not have enough color range. If you want a transparent background, I will vote for the PNG. If you want a file with a small size and with a good range of color, it's gonna be the GPG. The reason why the GPG is used in the mobile phone is because usually you're gonna take an image and you want to send it. So that's why they wanted to increase the range of the color, and also at the same time to decrease the file size. Sound representation. Computer, as we said, is capable of representing number, text, images, and also sound. But more complex data like the sound and the movie are requiring more additional technique and algorithm. So in regard to sound, it must be represented in a finite way using binary code. And the sound is inherently analog and usually represented as a wave. And all of us know that sound have the multiple sound could have different amplitude and different frequency, as we can see with all these different music devices. When we were using the cassette, we were recording using the analog signal. But if we want to record an analog signal, we cannot produce it exactly. And it wasn't a problem because the human ear cannot notice these inconsistency in the sound recording. But if we take this recorded cassette and we make a copy from it, and then this copy, we take another copy from it, and we copy it using the analog copying that was used, the error produced and the first copy will be propagated to the second copy, and the error will increase, and then in the third copy the error will increase more, and then we gonna notice the difference. If you ask your family member who were using the cassette, they might tell you that we can end up in some time with a cassette that we cannot understand what's the person saying on it. That's why we end up with a shift to digital recording. Digital recording can be reproduced exactly without the extent that we will arrive at damaging the sound quality. How the digital recording happen? By taking the analog signal, we take the analog signal and we try to get a discrete value from this analog signal using a process called digital sampling. So what is a digital sampling? The digital sampling is the process in which an amplitude of a wave is measured at regular interval and stored at discrete measurement. So again, when I talked about the analog signal, I said the analog signal is consist of infinite value. So for any small period of time here, we can get a value here, and this is gonna be infinite because of the continuity of this wave. In order for us to represent this analog signal in the computer, we need to come to this wave, and we would say like we want to take a specific sample and we're gonna measure the amplitude at this specific sample. So for me, I would know at this time that this is the value of the wave, but what's about the value in this part, we wouldn't know exactly, so we will lose some information, but we can get this information or value through estimation. But anyway, this is happening only one time, and then we have a discrete value, and these discrete value can be converted to 0 and 1. So this is how we can convert an analog signal to digital signal. So with digital sampling, we are taking some point at a regular interval, like for example here, and for making sure that we are not losing a lot of information, we're gonna try to make the interval smaller to be approximate of the analog signal, for example like this. Then we're gonna measure the amplitude at this point to get the value, and then we're gonna get the discrete value that will enable us to store them in the computer. Similar to the image, a file also use compression format, because if we try to make them to if we try to capture the digital recording as close as possible to the analog signal, the file will be large in size. So there is obviously many file compression format available, but the two main file standard known are the WAV and the MP3. WAV is an example of a lossless compression format. This means the recording is reproduced with any loss in audio quality. So when we are saving the file on the computer using this format is the same way we did the digital sampling, we're gonna store it. Therefore, the audio file is gonna be large in size. In regard to MP3, it's a loosey compression format. That's mean like in when we are storing these discrete value in the computer, we might end up with removing some information to make the file size smaller. And usually the MP3 will try to remove information that's not gonna be easily identified for most average listener. But again, as I said, this is gonna reduce the file size. MP3 is easy to distribute over the internet or to store it in the cloud. This is the main reason why MP3 has become a standard for purchasing music over online, or even use in portable device like the device here, MP3 player. So if you go to iTunes or Spotify, usually you will find the file in MP3. Now let's talk about movie representation. In principle, a movie is actually a sequence of images. If you're gonna look at a movie of person talking about a specific topic, you're gonna see that it's actually a sequence of image of the same person talking where his lips is moving, but usually if he is standing in a still background, everything else is the same. These sequence of images, we call them frames, and they are produced or displayed in sequence to produce the effect of motion. Uh, so the movie is displaying this frame, the sequence of image, at a rate faster than the human can notice. That's why we see it as a movie and something moving. Uh, each frame is an image of a scene taking a fraction of a second later than the previous frame. Usually, a movie can take a frame 24 per second or 32 a frame per second. The number of frame per second will be higher if the movie is an action movie and you want to see the detail of the moving. So if we think about slow motion, usually in a slow motion movie, the frame per second will be higher because we are trying to capture something fast, something that's happening at fast, but in a way that we can see all the detail of it. Again, the frames are displayed at the appropriate rate to produce the motion picture on a screen. So the amount of a frame that are taking per second, it's gonna be appropriate to produce the motion that we want on the screen. The most common format for movie are MPG or MP4. And the most and which are using variety of technique to compress a video. So as we said, images are consisting of multiple frames where each frame is actually an image, but the difference between the frame and the image is usually these frames are kind of similar, like you could have 24 frame in a second which are kind of similar. The only difference is like a moving of the lips or the hand of a person. Because of this reason, in order for us to compress the image, each individual frame use techniques similar to GPG to make the frame size smaller in the disk. And also by taking the advantage that most of the time the frame are similar, the only thing that these compression format MP4 and MPG are doing is instead of saving the entire image, they only for example save the first image, the first frame, and then in regard to second frame they can only save the difference between them. In reality, actually, images are represented using a matrix, and with the operation of the matrix we can take the difference between two images easily. So the matrix is the same as the grid that we saw representing the pixel. So this is gonna reduce the redundancy, and if we are reducing the redundancy, that means we're gonna be able to reduce the file size. While the compression rate depend on the content of the movie, but storing to our movie is roughly 500 megabyte, where 3 kilobyte per frame in MPG format. So using MPG or MP4, we are able to store to our movie in roughly 500 megabit, while maybe other megabyte, while other format could store to our movie in 1.5 gigabyte. Again, this is gonna depend on the content of the movie. If the movie is about a person who just speaking and he's in the same location, the compression rate will be more. But if the movie is going out from different scene to another, and the movie has many frame and it's in HD and better and more pixel, the number will be different. Also, the movie are stored in physical format like the DVD and Blu-ray. DVD are usually used to store a standard movie, and the standard movie have a resolution of 720 multiplied by 480. The capacity of the DVD is in single layer 4.7 gigabyte, in the double layer is 8.5 gigabyte. Blu-ray is used to store high definition movie and full definition movie. So the resolution could end up to be 1920 by 1080. So, by the end of this lecture, we understand that the computer represent all these kind of data using binary code. But how the computer know the type of value stored in particular piece of memory? The short answer, the computer does not know, because when we explain in this lecture, with one bit I can represent 0 or 1. 0 or 1 could be the number 0. 0 in binary as a code could be number 0, or could be a color white. As the example here, this bit pattern here, if encounter, the computer might represent it as the integer 97, or the character A in small, or even a fragment of image. So how the computer know what type of data it is? When we are storing the data, or when any program try to store data in memory, it must store additional information, and this additional information will let the computer know what is the type of data. So again, the same bit pattern may represent different value in different contexts, and you can use this website here to put a binary number up to 32-bit, and it's gonna give you all the possible value in the data. Like for example, it's gonna give you here in decimal, single precision real number, and an ASCII text. So I would advise you to use this website to check if your answer for the conversion of binary number to decimal is correct, but to try first to do the conversion in hand. Use this application or this website only to check the answer, because as you see in this last slide, is we are asking you to convert from binary to decimal. So try to convert this number from binary to decimal using the procedure we explained in the lecture, and after you get the value in decimal, put this code on the previous application here and check what is the value will be in decimal, and you might notice that it's actually also represent any another data type. You can also use the ASCII table to find the binary code for each of the following text. Thank you so much.